Since in lesson number 2, we mastered the 5 standard form categorical logic templates using just 3 categorical terms, a major term, a minor term, and a middle term. And we're able to plug those into any of the 5 known valid templates to produce a conclusion by necessity from those premises. That was in lesson 2. Lesson 2, I know it was a bit of a climb, but it was worth it. Here in lesson 3, we're going to examine the methods of demonstrating the validity of what are called propositional logic arguments, sometimes called statement logic, sometimes called symbolic logic. All of that will make sense to you after this lesson today. Now, categorical logic that we mastered in lesson number 2 was very effective for the study of law, philosophy, ethics, politics, economics, in general. I mean, any general argument, morality, religion, would be fine to use categorical logic because it usually only involves a couple of terms. But what about arguments that involve hundreds of terms, even thousands of terms, as happens in computer programming, for instance? Well, thankfully, we have propositional calculus. It's sometimes called propositional calculus, by the way. Symbolic logic, statement logic, all meaning the same thing. This is when we take ordinary language statements and we use logical operators, if, then, not, and, or, if and only if, logical operators which are proven valid by truth tables when truth values are assigned to the propositions themselves. We'll see that when we cover truth tables today. The advantage of propositional logic is that we can take ordinary language and then translate it into symbols. By the way, an advantage of that is that we release any emotive attraction we might have to the ordinary language just using symbols, as we do in mathematics, for instance, to build a house, or geometry to lay out a concrete driveway. We use symbols to think. Scratch any mathematics and you'll find logic underneath, especially propositional logic or symbolic logic. And that's why mathematics is such a value to scientists. They use it all the time. Thousands of propositions have to be checked for their validity. So we're going to show you, first of all, how to translate from ordinary language. We have one in the textbook. How to translate the ordinary language about who's the mother of a baby. And we're going to translate that from ordinary language to symbolic logic. And then we're going to apply just five of the 19 rules of natural inference to prove the validity of the argument that's in the textbook. And we'll show you how that happens step by step to construct a formal proof, which is what is necessary if you're going to apply propositional logic to any career, any academic discipline, any procedure at law or justice, or even ethics and morality, even theology. So we'll show you how to do that. And then we'll give you 2 shortcuts. Actually, we'll show you the long formal form today, and then we'll give you 2 shortcuts. The 2 shortcuts are conditional proof, which is where we assume the antecedent of an if-then statement, just for the sake of argument. You've heard that expression before, just for the sake of argument. Well, that's where it comes from. It comes from propositional logic, conditional proof. Then we're going to examine something called truth by contradiction. That's when we assume that the conclusion is false. And then we test the syllogism to see whether or not we can prove that the conclusion is false. Interesting. Lawyers use this in court, as we will see today. So first of all, let's share the screen and look at the argument that we have already prepared that's in our textbook. By the way, for lesson 3, this lesson, you'll be using the textbook a great deal, more so than you did in previous weeks, more so than you did in previous lessons. So everything that you need to know and everything that you need to learn is right there for you. I can't give you everything here in just 1 week out of 4. That's why you have the textbook. You're a lifelong learner. Otherwise, you wouldn't be here. You can handle it. You can deal with it. You can master this on your own. I'm simply going to give you the basics of how to do this. So let's share the screen, shall we? So here we are. Here's the argument that we have in our textbook. Just use Control F to find it if you want, and use one of the names of one of the people here for a very quick search. Anyway, get to the book, but follow it along here for this lesson. And here it is. Here's the argument in ordinary language. Let's suppose somebody said to you, you know, if Alice is the baby's mother, then Brady is the baby's father. And if Brady is the baby's father, then Chuck is the baby's uncle. And if Chuck is the baby's uncle, then Lydia is the baby's aunt. Oh, but Lydia is not the baby's aunt. Oh dear, oh my. Oh. So either Alice is the baby's mother or Ellen is the baby's mother. Therefore, Ellen is the baby's mother. Now, it's not immediately obvious to me or to anybody reading that ordinary language for us to tell whether or not that's a valid conclusion that Ellen is the baby's mother. So just by invoking 5 of the rules of inference from propositional logic, we'll prove the validity of this argument. So what we're going to do is we're going to translate each of those premises that we just read into symbolism. So the first premise, if A is the case, then B is the case. If B is the case, second premise, then C is the case. Third premise, if C is the case, then L is the case. Fourth premise, not L. L is not the case. Lydia is not the baby's aunt. Very important because it allows us to apply the rules and to dissect the argument and to see whether it's valid. Step 5, premise number 5 is either Alice is the baby's aunt or Ellen is, either Alice is the baby's aunt or Ellen is the baby's aunt. Therefore, Ellen is the baby's aunt. Well, here's what we do in a formal proof. After we have translated the ordinary language into the symbolism that you see right there, then we go to step 6. We write out step 6. So we go, let's take a look at premises number 1 and premise number 2. That looks familiar. That looks just like what? A hypothetical syllogism, one of the rules, one of the 19 rules of inference. And what do we get if we apply a hypothetical syllogism to premises number 1 and premise number 2? Well, we get that A implies C. That's exactly what step 6 says. We derive A implies C from premises number 1 and premise number 2. So if A is the case, if A, then B, if B, then C, that means that if A, then C. That's what a hypothetical syllogism does. Okay, so how do we, step 7, how do we, now that we have that, we move on to step 7. Step 7 is that we can derive, if A is the case, then L is the case. How do we do that? Well, from premises 6, the one we just did, and premise number 3. What's premise number 3? Premise number 3 is if C is the case, then L is the case. But we know that not L is the case from step 4. That's one of the given premises. Oh dear. So step 3 and step 6 we derive that this is the case. So by invoking the hypothetical rule, we're able to proceed in the argument to show its validity. Step 8, not A is derived from premise 7. What's premise 7? If A, then not L. And 4. And 4 is what? Not L. So we're able to derive not A by invoking modus tollens. That's one of the 5 rules that we're studying. So now we move on to work on premise number 4. We know from the valid argument modus tollens that if L is false, then A must be false. Recall the argument from modus tollens. If A, then B, not B, therefore not A. Well, there we are. So this leads us to the conclusion. Step 9. E, the conclusion is derived validly from premises 5 and 8. 5 and 8. There's 5. And there's 8 right here. Okay. Either A or E, not A, therefore E. So that's what a formal proof looks like, translating from ordinary language into propositional symbolism and applying just some of the rules, just a couple of them. Now imagine that this argument went on for thousands of lines of premises, thousands, as you would have in a computer coding, software coding problem. So that's something that is in the book. You can follow it again and study it, because this is how you take ordinary language, translate it to propositional symbols, and then apply the symbols of the 19 rules, in our case only just 5 rules of symbolic logic, and you're able to prove the validity of any argument. Now this would be handy for you working through marketing, advertising, education, even economics. But when you're getting into mathematical problems, when you're getting into computer science problems, you're going to be using propositional calculus. That's another name for propositional logic, propositional calculus. So remember, I promised to discuss with you and show you what a truth table is, because propositional logic used to rely only on truth tables before computers. Used to rely only on truth tables to prove propositional logic arguments. Now, what I'm going to show you is a truth table that demonstrates the conditions under which the logical operator or the wedge, the symbol of the wedge, is actually a valid inference if and only if the propositions P, Q, and not P are involved in the argument. So we're just going to look at this truth table now. And here you can see this is the truth table for the logical operator or. And what this truth table does is it provides 4 lines. Each of the lines assigns a truth or a falsity value to these propositions: proposition P, proposition Q, and proposition not P, not P. So on the second line, if P is true and Q is false and not P is false, then this is a false indicator. So the second line defines the logical operating conditions under which not P or Q would be the case. So in the other 3 lines, it's all quite valid. But if this is the case, if you have this line, if you can prove that proposition P is true, proposition Q is false, and proposition not P is false, then the logical operator does not work. It doesn't operational, right? So that's what a truth table is. Now, can you just imagine that instead of just 3 propositions here, P, Q, and not P, can you imagine an argument that has thousands of lines of code, thousands of logical operators all working, including just this one here? But all of the other operators, the negation, the conjunction, the disjunction, modus ponens, modus tollens, hypothetical syllogism, De Morgan's, all of the 19 rules involved, which were worked out on truth tables a long time ago. But today, computers do a much better job. Computers they do not know about ambiguity. They do not tolerate ambiguity. Computers do not tolerate contradictions. They do not tolerate contraries. Logic is the police officer of science and of logic. And if you violate any of the rules of logic, your argument fails. It is invalid. It is invalid, invalid, same word. Right? So that's what a truth table is. We're not going to drag you through kicking and screaming through constructing truth tables for 15 propositions and 19 logical operators. We're not going to do that. That's for undergraduates who have like weeks to do this sort of thing. We're going to move on to two other methods of actually they're shortcuts to doing the formal proof that we just did. So we're going to move on here to two things. One is called conditional proof and the other is called proof by contradiction. So here we go. So rather than constructing long lines of truth tables, we'll let computers handle that for us. They do a better job. We have what's called a conditional proof. Now, a conditional proof is a quicker way to validate the use of any conditional test for invalidity. So we're going to test for invalidity this time, not validity. And the conditional proof is when the assumed antecedent of a conditional if P then Q, the antecedent being if P, is assumed. There's nothing wrong with this. It's called the conditional proof assumption sometimes. The goal of the conditional proof is to demonstrate that the conditional proof assumption is true. Then the desired conclusion necessarily follows. But if we assume the antecedent of the conditional to be true, and it turns out that the argument results in a false conclusion, then we know that we have made a mistake and that our argument is invalid. So here's what a conditional proof would look like. I'll just read it off, as you can see on the card. If P is the case, then not Q is the case. First premise. Second premise is if R is the case, then Q is the case. The conclusion would then be if P is the case, then not R is the case. Well, how do we derive that conclusion using conditional proof? It's a simple proof. It's a simple argument. So it's relatively easy to see just using modus ponens and modus tollens. So what are we going to assume? We're going to assume this. We're going to assume P, because that's the antecedent to the conditional, if P, then Q. So we're going to assume that. So you write that in your formal proof off to the right-hand side here. I'm assuming that. You're letting people know you're assuming that. So if you're assuming P, then you can what? You can generate not Q. There you go. How? Well, 1 and 3. 1 and 3. So we're going to take 1 and our assumption, and that gives us not Q. Then what do you do? Well, if we take the second premise, if R then Q, and we have already got not Q from our first operation of 1 and 3, then we can use modus tollens to derive not R. Now, if we have not R by conditional proof, if P then not R, we have proven the conclusion. So that's a pretty short way of determining the validity of the argument. We're going to move on now to the second method, which is called proof by contradiction. Very, very interesting thing. So what do we mean by proof by contradiction? This seems to be kind of sketchy, but actually it's not. Lawyers use this all the time. You've probably seen it on many TV shows and movies, proof by contradiction. So here's an example here that I provided for you. Proof by contradiction. Well, suppose, for example, a man is accused of holding up a bank, and he can prove that he was at someplace else at the time the crime was committed. He will certainly be cleared. The logic of his defense is as follows. So his attorney would simply introduce this. Suppose I did commit the crime. Let's suppose you're right. Suppose the prosecution is correct. Then at the time of the crime, I would have had to be at the scene of the crime. You're not saying I hired other people to commit the crime. You're saying I committed the crime. So you're saying that I was there at the crime. Well, okay, let's just say that your assumption is false. Well, in fact, at the time of the crime, I was meeting with 20 people far from the crime scene, and that they will so testify. This contradicts the assumption that I committed the crime, since it is impossible to be in two places at one time. So he has reduced the prosecution's argument to absurdity. Reductio absurdity. Reductio ad absurdum is one of the other names that is used for proofs of contradiction. So I want to just point that out to you. If you can demonstrate that the argument itself is self-contradictory, if we assume the conclusion to be true, assume the conclusion to be true, does a contradiction follow from the given premises of the argument? If so, we have successfully employed the proof by contradiction. Very, very useful. All right, that completes lesson number 3 for today. And what have let's just summarize what we have covered today. First of all, we've understood the difference between categorical logic and propositional calculus, propositional logic, symbolic logic, statement logic. They all mean the same thing. I don't know why they do that. They should just pick something and stick with it, but they do. So we also looked at the procedure for taking arguments that have several premises, several terms, more terms than just 3 from categorical, several terms, many propositions, and how to translate that from ordinary language into propositional calculus. And so we walked you through the argument that's actually in the textbook. You'll want to review that. Then we took a look at truth tables. And we quickly decided that using truth tables as a method of verifying long, thousands and thousands of lines of propositions and logical operators is better suited for computer technology than it is for human beings. And thankfully, we have that. Okay, logical operators should be studied by you in the book, because they each truth table that I put in the book shows you how to validly indicate what line of the truth table defines the logical operators and or negation, if, then, if and only if. All right. So those operations will be usefully use the truth table to understand at least what the truth table is. Then we took a look at the conditional proof. The conditional proof is where you just assume the antecedent of a condition to see whether or not you can still generate the conclusion. If it does, well, you've saved yourself a lot of time and effort. But you have to be methodical and careful that you don't take any shortcuts. And then we took a look finally at proof by contradiction, used in courts of law, used in advertising, used in many educational environments. If you can prove that by assuming the conclusion of a given argument, that given argument is self-contradictory, well, then you have reduced that given argument to an absurdity, because logic does not tolerate absurdities. So that's what we have done. So all of this, folks, is preparing you for week number 4, which is the payoff that you've been waiting for this course. In week number 4, we'll show you how to use all of this technology, all of this reasoning and logical technology of categorical logic, symbolic logic, statement logic, conditional proofs. All of this will show you how to use this to, first of all, make a valid argument, and then show you how to refute a valid argument. As you know, from now, not every valid argument is a sound argument, meaning that not every valid argument has factually true premises. So we'll show you how to discover factual truth and to propose alternative valid arguments to whatever is under debate. Remember what I said in a previous video, that the person who wins the debate is the person who gets the other side of the debate to accept their definitions of the terms of the argument. That's what I learned the first day in high school in debating class. And believe me, it has always been the case. Anytime I'm able to get the other side to accept my definitions of the argument, I'm going to win that argument, because then it's just, it's just bring out the technology of validity and chop, chop, chop. So use the book extensively and be prepared for that. And then next week, we'll be able to apply all of this. Thank you very much for your perseverance and your persistence. You're lifelong learners. Otherwise, you would not be here. And it's a joy to be with you. Thanks.